Jnanam Paramam Dheyam. Knowledge is supreme.
Now, let us move on to the next topic of discussion. We have taken a holiday from symmetry for a couple of days. Now, that holiday comes to an end. So, we go back and we discuss the symmetry of electronic states. When I say symmetry of electronic states, I mean symmetry of the total electronic wave function, okay, spatial part, not total, spatial part of the electronic wave function. Let us see what it means. And why do we need to do this? We need to do this because we go back to our old friend transition moment integral. If Born-Oppenheimer approximation is valid, if you can separate vibration from vibrational part from electronic part, you know very well that this is how we write the transition moment integral. Psi v dash, psi v integrated over all space, psi es e dash test dash maybe mu psi es integrated over all space, or maybe we will write this separately as well, integral psi e dash mu psi e over all space multiplied by integral psi s dash psi s. We have already dealt with this last week and we have arrived at what is called the spin selection rule. We have dealt with this and we have got Frank-Condon factor. What we now want to talk about is this part. This is what gives us what is called the orbital selection rules. Very briefly, we had said yesterday that this is what gives rise to your familiar Laporte selection rule. But what we now want to do is we want to do a more systematic discussion of this orbital part of the transition moment integral. And since we have discussed vibrations already, we know that for what did we do for your vibration of polyatomic molecules? We talked about the symmetry of the vibrational wave functions and use symmetry to evaluate whether the transition moment integral is non-zero or not. We will adopt an exactly same strategy, identical strategy for the electronic wave functions as well. Okay. So, you see, three terms is what we are talking about. One term is something we know already, your transition moment integral x, y, z. Okay. All we need to understand now is what are the symmetries of this and this, the wave functions, electronic wave functions. To do that, first thing we need to understand is how do you write an electronic wave function. Suppose you have some electron configuration, you have several orbitals, let us say maybe I will write those orbitals as phi and the electronic wave function overall as psi. Let us say I have orbitals phi 1, phi 2, phi 3, phi 4, so on, so forth, right. And let us say for now I have one electron in each. Okay, of course, that is not going to be ground state at least. So, let us say this is the configuration phi 1, 1, phi 2, 1, phi 3, 1, so on and so forth. You understand what I am saying? Electron configuration. Of course, the phi's are MOs, do not forget that. When I say orbital, here I mean molecular orbital, we are discussing molecules, not atoms. So, psi will be of course phi 1 multiplied by phi 2 multiplied by phi 3 and so on and so forth. So, if the electron configuration is phi 1 2, what will psi be? I have 2 electrons in phi 1, that is all I have, it is hydrogen. What is the, come on, you have done this actually. What is the electronic wave function for hydrogen, dihydrogen ground state? Huh? What is the electronic wave function? Yes? 1s dihydrogen is what I am saying. Yeah, so whatever is the bonding orbital, right. So, there your 1s comes in, 1s plus 1s, that you multiplied twice, right, and then you wrote the wrote electron 1, electron 2 and then you proceeded. So, the thing is So, in that case all I have to write is 2 is equal to 1, nothing else. So, this is how you write the wave function. I think we are all familiar with that, with the product of the electronic wave function is given by product of the molecular orbitals. So, what is the symmetry of the electronic wave function? If I say this is the representation of the electronic wave function psi of the molecule, will you agree with me that it is gamma 1 cross gamma 2 cross gamma 3 and so on and so forth? I take a continued product of the symmetries of the molecular orbitals that are involved. Okay? So, now this is all that we need to understand, to be honest. Whatever we discuss for the remaining time today is based on this. Okay? So, let us start. We are going to arrive at I think 5 rules. Now, depending on how I frame it, 5 can become 3 or 6, but I think 5 rules. This part of the discussion is from Harris and Bartolucci. Okay. So, this is discussed very nicely there, it is very easy. Alright. So, this is this is what you have to remember, we take direct product, but then things can get complicated as we go along. So, first thing, what happens when I have a molecular orbital that is doubly occupied? No matter what the symmetry of that molecular orbital is. I have one molecular orbital, I have 2 electrons in it. What will be the symmetry in such a scenario? Yes? For that, we will need to remember a small theorem or working formula that we had derived in the previous classes, and that is in the syllabus for tomorrow's quiz. So, you better be able to say what it is. What happens when I take a direct product of something with itself, some symmetry species with itself? What do we get? We get the totally symmetric representation. Does that ring a bell? Totally symmetric representation. So, see, fully occupied orbitals, that is rule number 1. Doubly occupied MOs they give rise to a totally symmetric representation. What does that mean? It means that when we talk about any molecule, we do not really care about the core, right? Only the valence shell matters. Is that right or not? Say not only the not everything in valence shell matters. All MOs that are doubly occupied, almost all MOs are going to be doubly occupied, right? Think of any say diatomic molecule. Dihydrogen, well, dihelium if it is there, then what is there after helium? Periodic table, let us see how many of us remember. Hydrogen, helium, lithium. If I have dilithium, okay, all orbitals are doubly occupied, right. So, for all these the ground electronic state is totally symmetric. What is there after lithium? Beryllium, right. All orbitals are doubly occupied in Be2 as well, is that right. What is there after beryllium? Boron. What is the case for boron? Doubly occupied. Carbon. What about carbon? Achha, do not forget that there this sequence also matters. Where are we going to get a complication? There is no problem anywhere except for oxygen. In oxygen, you will see that there are 2 electrons, but they are in 2 degenerate orbitals, right. So, in the simplistic picture that we write 2 arrows like this, right. That is where we will need to expand our discussion a little bit. Before that, whatever ground state we have for diatomic molecules, homonuclear diatomics, they are all totally symmetric. Are we clear so far? Alright. And even for oxygen, everything except for those 2 electrons in the pi orbitals are in orbitals that are doubly occupied, right. So, we do not have to worry about all those orbitals. Totally symmetric cross totally symmetric is totally symmetric, okay. That is the main idea that we need to understand. Of course, what happens when there is one electron, a single electron in an orbital? So, I hope we have not forgotten the symmetry of the MOs. Remember, we had worked out the symmetry of the MOs. Let us draw it once again. What is the lowest energy molecular orbital? It is formed by linear combination of two 1s orbitals, right. So, if we want to draw a rough sketch, this is how we draw it. What is the symmetry of this one? Of course, for that we will need to have a look at the appropriate character table. What is the, if you are discussing homonuclear diatomic molecules, what is the symmetry point group? What is the point group of a linear homonuclear diatomic molecule? Well, the answer is in front of you, d infinity H. Who will say H? H. Oh, that H went into the tail of your speech, so I could not hear. This is the character table, right. So, for this sigma g plus is the totally symmetric representation. So, everything is sigma g plus, alright, and not only it is not enough to say sigma g plus. So, ground state of say dihydrogen, we write it as sigma g plus and we write a small 1. How do I read this? Singlet sigma g plus. Why singlet? Because spins are paired, okay. But of course, when I say spins are paired, do not forget what I mean. I mean alpha beta minus beta alpha, please do not forget that. We are going to use that also. You will understand what I am saying. When I say singlet, I mean alpha beta minus beta alpha, please do not forget that. Do not get too obsessed with this and this picture, okay. So, singlet sigma g plus is the ground state of things like dihydrogen, dilithium, all those things. Let us say, why is it singlet sigma g plus? Because the symmetry of this orbital is sigma g plus, right. Sigma g plus cross sigma g plus is like that. So, I have written this as small sigma g plus, I have written this as capital sigma g plus. This is the convention we are going to follow. When we talk about orbitals, we will write sigma g plus. When we talk about the state, when we talk about orbitals, we will write small letters. When we talk about the state, we will write capital letters, okay. Today's discussion will mainly focus on homonuclear diatomics d infinity H, that will familiarize ourselves, that will familiarize us with this character table as well. But then tomorrow onwards, we will actually use simpler character tables as well. Now, but then in any case, let us go ahead a little further. Let us say I am talking about the ground state of benzene. So, what will be the ground state of benzene? First of all, singlet or triplet? Let us think only about the pi electrons, forget sigma. Singlet, right, all spins are paired anyway. Of course, writing the spin wave function in that case is not as easy as alpha beta minus beta alpha perhaps. And what will be the symmetry of the state? For benzene, it is not sigma g plus, right. I agree with singlet. What will be the totally symmetric representation for benzene? A1G. So, for benzene, the ground state is singlet A1G, alright. And when I write things like this, those of you who have studied term symbols will perhaps recognize that these are the terms in term symbols, alright. So, I had a chat with some colleagues and I have been told that in inorganic chemistry they discuss LS coupling term symbols in some course, I do not know in which course. So, I will not try to do that. All I want to say is this term symbols that we get from symmetry and term symbols that we get from LS coupling and all that, they are actually the same. The reason being that there what you do is you try to use the vector model of angular momenta and think of how they couple, okay. How they couple depends intricately on the symmetry of the electron cloud, you can think, okay. That is why they are actually one and the same. I will not elaborate upon this further because we are supposed to learn it in some other course, but we will go ahead with how to find out the terms from symmetry, okay. So, these are the terms: singlet sigma g plus in case of H2, singlet A1G in case of your benzene. What about helium 2 if it is there? For helium 2, what is the symmetry of this orbital? Character table is there. What is the symmetry of this? We had done this earlier. But first thing to ask in situations like this, G or U? U, definitely U, right? And it is, what will it be? Some kind of sigma, of course, some kind of sigma U. Which one? Sigma U minus or sigma U plus? Why sigma U minus? This is 1, C infinity is 1, fine. The difference between sigma U plus and sigma U minus is here. When you apply sigma V, where is sigma V? This is sigma V. What is the character, plus or minus? Plus, agreed? Right. So, there is no need to be so negative, it is plus. But let us check the others as well. Well, others there is no, it does not make sense because they are all the same. The difference comes from sigma V. So, this is actually sigma U plus. What is the ground state of helium? Sigma G plus cross sigma G plus, that gives you sigma G plus anyway. What is sigma U plus cross sigma U plus? That is also sigma G plus, isn't it? So, that brings us back to this. When you have all doubly occupied MOs, then it is a totally symmetric state. Alright. Are we all clear? Any question? Any question? No. Great. Let us get ahead then. Suppose I do not have helium 2 plus, I have helium 2, what about He2 plus? What will be the electron configuration in that case? Sigma G plus 2 and 1 electron in sigma U plus. So, what will be the symmetry of state? Sigma U plus. Simple? Simple? So, this ground state has singlet, singlet triplet, what will it be? Sigma U plus, I agree. What should I write here? Singlet or triplet or something else? What? I have one unpaired electron, the others are paired anyway, right? I have one electron, of course, it makes no sense saying one unpaired electron, unless you have two, where is the question of paired and unpaired? I have one electron, what is the spin state for that? Is it singlet, triplet, quartet? Yes? Yes, Nitai? 2, doublet. So, you can either have alpha or beta, right, 2 possibilities. So, it is a doublet, 2 degenerate spin states are there, alright. So, it is a doublet sigma U plus, do not think it has to be singlet or triplet always, singlet or triplet arise when you have 2 electrons, when you have a lone electron it is doublet always, okay. Okay. So, this is rule number 2, singly occupied MO, symmetry of state is the same as symmetry of MO, alright. Now, rule number 3 is you have 2 electrons in 2 non-degenerate orbitals. Of course, if you have 2 electrons in 2 non-degenerate orbitals, can that ever be a ground state? 1 electron in 1 MO and another electron in another MO, they are not of the same energy, that can only be an excited state, alright. So, before going there, let us remind ourselves what are the kind of symmetries we have. What is this? MO formed by combination of pz orbitals, this is bonding. What is the symmetry? What is the symmetry? Character of E is 1, character of C infinity 1, What is the next thing? Sigma V. What is the character for sigma V? 1. What is the character for I? 1 or minus 1? 1. Very good. Then this is the problem of using PDF file. What is the character of S infinity? 1, sure. And what is the character of C2? 1. So, it is still sigma G plus. Similarly, the antibonding orbital will still be pi sigma U plus. And what about the pi bonding orbital? What is the symmetry of pi? Well, symmetry of pi is pi. But which one? Pi G or pi U? Pi U, right? Are we clear about that? Now, let us talk about then an excited state, and well, we can choose anything, but let us say I have excited state of oxygen. What is the ground state of oxygen? Ground state of oxygen, what is the electron configuration? Pi G or pi U? That one, is it bonding or is it anti-bonding? So, that is pi G, right? Anti-bonding is pi G. So, ground state electron configuration will be pi G1, pi G1, we will come to that. But let us say I have performed a transition, okay. Somehow I have one electron in pi G, say oxygen, dioxygen excited state. This is the electron configuration pi G1 and let us say sigma U1. Somehow I have populated a sigma, anti-bonding sigma. What will be the symmetry of this state? The same rule applies. Now, first of all, you have to take a direct product of these two. What do you get if you take direct product of these two? In fact, you do not even have to look at the character table for this one at least. As Manthan is saying, when you have a product of Gerade and Ungerade, of course, it is going to be Ungerade. Is that right? Because Gerade or Ungerade depends on the character of your inversion, I inversion. So, it's for Gerade it is +1, for Ungerade it is -1, 1 into -1 is -1 Ungerade. So, it is Ungerade. Not only that, if you have sigma and if you have pi, what will the product be? Product will also be pi. Okay. Think of the character of E. Character of E is the dimensionality of the representation, right. Character of E here is 1, character of E here is 2, 2 into 1 is 2, actually it is pi U, and you can check here, this was pi G and what was the other one? Sigma, what did I say? Sigma U plus, sigma U plus, and we took pi G, multiply them, you are going to get back pi G, okay. If it is something else, it will just be the direct product. So, rule number 3 is take direct product. But tell me, how many states do I generate from here? First of all, I do not write pi U like this, I write pi U like this. For state it is capital, and will I get singlet pi U or will I get triplet pi U? This is the situation, I have one electron here, one electron here. Should I write singlet or should I write triplet? This case, can it be a doublet? No, right? 2 electrons, singlet or triplet. So, which one should I write, singlet or triplet? In this case, we can write both, right. When you have 2 electrons in 2 levels, then you get singlet states as well as triplet states, right. Because if you go back to the form of wave function, say this is phi 1, this is phi 2, how do you write phi 1 1, phi 2 2, but you can never just write that, you have to write phi 1 2, phi 2 1 as well, and you take linear combination plus or minus, right. So, you always generate special parts like this, say phi A 1, phi B 2 plus phi A 2, phi B 1, and you have phi A 1, phi B 2 minus phi A 2, phi B 1, alright. This special part is symmetric. So, that will be associated with what kind of spin parts, symmetric or antisymmetric? Why? And that is, which rule is that? Poly principle, not exclusion. Poly exclusion comes from poly principle, right. So, this will be your alpha beta minus beta alpha, that is singlet, and this can be associated with alpha alpha or beta beta or alpha beta plus beta alpha, that is triplet, right. So, both are possible when the two orbitals involved are non-degenerate. Okay. I will quickly write rule number 4 and then we have no more time. What is rule number 4? Rule number 4 is if you have one empty degenerate orbital, example, what is the electron configuration of O2 you said? How many electrons in pi g? Yes. How many electrons are there? 2, right. So, I will write O2 plus, then it will become pi g 1, right. Dioxygen with a plus charge pi g 1. What will be the symmetry of the state? Same symmetry as the orbital that is singly occupied. Okay. It is sort of whole formalism, it is not whole formalism. In this case it is straightforward because only one orbital is there, but suppose I had 3, how many total electrons can be there in pi g? 4. So, if all 4 are filled for oxygen, what will be the charge? Minus 2. If 3 are filled, what is the charge? Minus 1, right. So, in that case also symmetry will be the same as the symmetry of this orbital. So, in this case symmetry is going to be doublet pi g. So, same symmetry. So, that one vacancy you can think of it as one hole and it behaves exactly like the electron as far as symmetry is concerned, alright. This is how you determine the symmetry of states. Now, when you have 2 electrons in 2 degenerate orbitals, then the situation becomes a little more tricky because spin of one determines the spin of the other. They are not uncorrelated like it is for 2 non-degenerate orbitals, okay. So, there we need to actually consider the symmetry of the total wave function including the spin part, not everything will be allowed. So, on Thursday we will start with that, we will talk about oxygen and then we will go on to discuss the transition moment.